All right, now, if you turn the page, we got three more simulations. For each of these, what is the probability that x is greater than or equal to 3? I'm sorry?
Are they all 25 still?
Yes. The first one? Not 0. 100%. 25 out of 25 are greater than or equal to 3. Yeah? For the second one, 24 out of 25. For the third one, 24 out of 25. Are you guys with me that each one of these simulations had a different result? So what's the problem with simulation? It's not even that it's not always, it's definitely an estimate, period. It's an estimate of the probability versus an exact value of the, okay? But most of the time, they're pretty close. And in reality, what we could then do is we had a total of 100 simulations. And if you looked at them all, 95 out of the 100 simulations. So the more simulations we do, the more and more this is going to start resembling the true probability we're trying to get at. We're going to start with a conversation of what is probability. Now, I'm going to ask you guys this question, but before you answer this question, there are a few words you are not allowed to use to describe what probability is.
Probability?
Obviously probability, but the word chance, likelihood, odds. So between probability, chance, likelihood, and odds, you're not allowed to use those words. What is probability? The randomness of something?
How often something happens and the total amount of ways it can happen?
That seems like a good way to calculate probability. But what is it? This feels icky, right? You know how many times I start with what does it mean to say, for instance, this is a 20-sided die. So the probability of rolling a 1 on this is 1 in 20. It didn't happen. See? Okay. And I'll say, well, what does it mean for something to have a probability of 0.05? And students will say, well, that means the odds are 0.05, which technically is not true. The odds are 1 to 19. But or they'll say that's the likelihood, and then I say, what does likelihood mean? You know what they say? Probability. It's the probability something happens. We use the words chance, likelihood, and probability interchangeably, but we don't really understand what they mean. Oh my gosh. It wasn't one. It did run into something. 11? Man, all of them have been so close to each other. I wonder what the likelihood of that is. They roll 1? No. What if I roll this one? 100. This is a D100, which was accurately predicted this morning in 4th period. 20.
How does it stop?
20. It does eventually stop, but it takes a while. Like, I'm going to keep lecturing while we wait for it to stop. It's not. Oh, it's a 1.
It's a 1.
It is a 1.
But the 1 is bigger than all of them.
Technically, the 100 is, right? Because that's the side that was on the bottom. Do you think it'll be a 1 again? Yes. 100%. It's a 50-50 chance. about to kick you out of class. So, if I asked you to define any of these words, right now are we feeling a little bit icky about trying to come up with an explanation of what those words actually mean?
Yeah.
Okay. All right, so here's what we're going to do, a nice little thought experiment. We are going to roll some different sided dice. I have all sorts. You know you can order a pound of dice from Amazon? So I have so many good dice here. I have a four-sided. Has anybody ever seen a four-sided die before? So with a four-sided die to roll it, that came up 3. It's actually the point at the top, so it's not the sides that have numbers, but it's the vertices. I think that one's cool. I got the D8. Oh. D20. I got the D10, D12. You guys get the D12? And here's what we're going to do. Sylvia, I'm going to have you pop back with Sophia here. Okay? You guys. In probability, we have events. We're in probability models. We have events and we have outcomes. So an event is a chance process. And an outcome is a possible result of said chance process. Okay, so here's how we are going to define our event. Our event is going to be a roll of a dice. Everybody's got, you guys each have different ones, yeah? All right, so in that roll of the dice, the way we are going to define our outcomes, we can define them lots of different ways, right? It could be, for instance, in this 8-sided one, it could be one outcome is a 1, one outcome is a 2, one outcome is a 3, right? But couldn't I define these outcomes as odd or even? Sure. This one was an odd. This one was an even. Yesterday we defined 1 as winning and not 1 is losing. You guys with me? So a chance process has different outcomes depending on what we're looking to do with that chance process. Okay. The outcomes we're interested in this particular chance process that I'm going to have you guys do are 1 and not 1. Now, whose dice has the highest probability of being a 1, or which of the dice? We had a D4, right? Okay, and we have a D8. That one, right? We have a D12 or a D10, D12, D20. Did I give anybody a D6? You get the D6, okay? All right. And are you guys with me? Highest probability of rolling a 1, lowest probability of rolling 1. Okay. So to explore what does it really mean to say something has a probability, what we're going to do is do some rolling. So at tables, whatever, I want you guys keeping track. I want you to do at least 50 rolls.
Of keeping track of how many are ones and how many are not ones.
1 versus not 1, 50 rolls.
Okay, we'll keep track of all these. Okay. So one's gonna have 11. 6. Okay, well, I'm gonna need 2 more. 7, no. 1.
Wait, no, 5.
I'm not even didn't do it.
Wait, what is it?
The Fibonacci spiral. The Fibonacci sequence goes,
So still 2 out of 50.
so what?
Okay.
11 now out of 50. Yeah, that's what I have. It's a
So you
thing,
just add whatever the ones.
the previous two. And so,
No, there's 7.7% chance I just don't get one.
1 inch square, 1 inch square, 2 inch square, 5 inch, 3 inch square, 5 inch square. That's a very famous pattern. Like if you
Yeah, but.
take it out as far as you can, which you can't because it can go on forever. But like, so 2 over 1, 3 over 2, 5 over 3, 8 over 5,
My old squad, like my 260 pounds.
etc. That approximates a number called phi. Phi,
I brought some more.
Like pi, but with an F.
Dad grew up on 8 times on one.
like pi with but with P because it's Greek. There's no F in Greek. This is the Greek F. This is the Greek F.
It's also very similar to in Russian. It's really
These, this spiral
At one point,
is the same spiral that makes like shells that are spiral and
It's like Y.
it's so it's more of a someone noticed that it happens. And if you look at like so phi is what we call the golden ratio. Like if I were to ask somebody to draw me a rectangle, it is very likely they draw that rectangle in such a way that if this is 1, this is 5. Like it's a ratio of rectangles basically.
Is this 3D
And
printed?
like in architecture it shows up a lot, like if you look at like the Parthenon and all those kinds of things, like they all go at this ratio. If you look in nature, the Fibonacci numbers, like the number of petals on different types of flowers, are quite frequently Fibonacci numbers, as are in the pine cones and all that kind of stuff. You know, you can look in that, or like in a sunflower, you can start to see a spiral. It's the spiral. It's exactly what it is. All right, you guys have the D4?
Yeah.
How often out of 50 times did you guys get a 1?
11.
11 out of 50 times. Okay, and then D6, how many times did you get a 1?
7.
Got it in the D8 group?
3.
3? D10?
2.
D12?
5.
5? Okay. So I'm going to call that 1. Bzz, okay. So with one anomaly, are you guys with me? That what happened as we had those lower probabilities is the frequency of what occurs decreased. And if we did this 100 more times, I'm not going to make you do it 100 more times. These almost go down together, yeah? Right, like if we did this 100 more times, this group is, you guys aren't going to have as many, right? Like it'll even itself out. Okay, so, but what if we all rolled it one more time? Do we have any idea what's going to happen? on that one roll? Like if I could take this one right now, do I know what's going to happen? If I roll it one time, I got no idea. If I roll it 1,000 times, do I have a pretty good idea of what I'm going to get? Do you guys get what I'm saying? Okay. So, chance behavior is unpredictable in the short run and very predictable in the long run. Now, for any one of these dice, could I ask you guys to find the probability of an outcome? Like this 8-sided dice, what's the probability I get an even number? 50-50, yeah. 4 out of 8, yeah. What's the probability I get a number that is less than 3? 2 out of 8. So calculating probability, and like simple probabilities is not something I intend to teach you. You're not going to get a problem that says, I have a bag with 5 red marbles, 3 white marbles, and 2 blue marbles. What's the probability you draw out of blue? You would get so bored if that's the kind of problems I would give you guys. If I gave you guys, let's put it this way. What if all I had you do was flip dice all day today? Would you have gotten annoyed with me?
Yes.
Based off of these numbers, could we estimate the probability for each dice?
Yeah.
More or less. And what would it be? So, like, if I asked you what is the probability of, say, this dice, I'm picking it because the numbers are lovely. 1 in 10 or 10%, yeah? And that was the D12, so we were hoping this one would be 1 in 10, but we get the basic idea, yeah? Okay. And if we did it more, we'd get more and more precise as we do our answer. Is everybody good? Okay. So the question of what is probability?
It's kind of relaxing, like the sound.
Fine, I'm going to give you times tables. You guys don't want easy. Easy is boring.
We could try it.
Easy's nice every once in a while,
I think you guys are fairly laid back days. Sort of.
It's like,
It's like
quiz
after
correction.
the
Test
test
correction.
we get to do what we like.
Yeah,
yeah, we get to correct our test the day after.
yeah. It's super laid back.
I feel like this class would be a lot worse because
I'm tutoring somebody from UA in this class right now. And it could be a lot worse. For sure. Okay.
And you had how many like stats classes?
I don't know. I'm just working with one student. Okay. You guys. So here's what I want you to know. Probability of anything, of any chance process is what goes in there is a number between, what's the lowest number you can get for a probability? What's the largest number you can get for a probability? 1. If you give me a probability that is bigger than 1, you got automatically an I. In terms of the E's, P's, and I's, saying a probability is bigger than 1 is a really, really good way to show me you know very little about probability. Everybody with me on that? Okay. It describes the relative frequency of the outcome in a very large number of trials. So, does it tell me right now if I roll this what the probability I'm going to get a 1? Does the 1/8 mean anything? Only if I do it a lot of times does the 1/8 matter. Everybody good? All right. So, a certain brand of cell phone knows that 5% of its cell phones are going to be returned for damage or something. Okay? And it costs them $1,200 to replace the phone. Okay? They charge for a warranty $60. How come they don't have to charge?
It's only 5% go bad.
Yeah. So, like, imagine 5%, we have 20 people in a room, only one of those 20 people are going to break their phone. Yeah? Now, you guys were supposed to say no. What's wrong with saying only one of 20, if I have 20 people in a room, are going to break their phone?
So it's less than 5%, right?
1 in 20 is 5%. Yeah? You guys, that's not a very large number of trials. Do you guys get what I'm saying? Okay, so this is okay in the mind of the company because a company has a large number of trials. And in this case, we would call that trial. They sell a large number of phones. They don't. So companies like this, and this is very similar to you guys, similar to how insurance policies work. Okay. Like a company, when they charge you for an insurance policy, knows that they're not paying out on many of the policies. Okay. So for example, if you have a car insurance policy, right, that costs the company earns some money from you, right? But not all of you are going to get into a car accident, right? So they don't have to pay. Some people pay money to the insurance company and get nothing for it. They just have been paying for their insurance. Some people pay money to their insurance company, they get in a car accident, and then the insurance company pays them. Do you guys catch? Is that making sense? And the way they decide, how much do I pay? Why do you guys pay more in car insurance than I do?
We're more of a risk.
Less experience.
It has nothing to do with your guys' experience or anything.
We're more likely to get the car crash.
What happens is, it's not even that you individually. They don't treat you as an individual. They look at your age group and they say, more teenagers get in car crashes than people in their mid-40s.
Isn't men's insurance higher too?
Yes, it seems sexist, doesn't it? Except for men, a higher proportion of men make insurance claims than women. Like, for them, it's a numbers game. Why is it that you get discounts on your car insurance for getting good grades?
If you have good grades, you're less likely to be like.
Students who get good grades get in less car accidents. The frequency is lower. The frequency of the company having to pay out is lower. Okay, so I want you guys to start thinking about probability is about the frequency in a large number of trials. I can't emphasize how frequently something happens in a very large number of trials. Everybody good so far? Okay, now let's talk about randomness. All right, let's say I have a coin. I'm going to flip it 6 times in a row. I'm going to add one more here. Yes, if I flip this coin 6 times in a row, are any of these the same outcome?
Yeah.
Depends on how we define our outcome. Okay. If I define my outcome where the order of them is important, none of these are the same. If I define my outcome as number of heads, then they are the same. So it just kind of depends on how we define that outcome, which will have an impact of what we do later. Which one of these is the least likely to occur? Nope.
About the same chance.
If we define our outcome where the order is important, that there's a difference between tails then heads versus tails then tails versus heads then heads, right? If we define our outcomes that those orders are different, these all have the same likelihood or the same probability. Now, let's say I flip this coin 5 times, and I'm going for my 6th flip. But I know that the first 5 flips were heads. Okay? What's the probability that the next flip is going to be heads?
50%.
It's still 50-50. We're comfortable with that, even though we already had 5 heads? But I thought it was supposed to even out to be about 50% heads, 50% tails.
You don't have data sample.
Okay, what if I did this? What's the probability the next one comes up heads or tails? It's still 50-50. Yeah? Okay, so once we've flipped the coin, these ones are no longer up to chance. They were before we flipped them, but they're not afterwards. Remember how we talk about probability is about a large number of trials. My next flip, how many trials is my next flip? It's only 1. Is everybody with me? Okay. Now, this is a concept that has gotten people into a lot of trouble because they don't understand it. And they say, hey, I'm up to bat again. I'm usually a 300 hitter. I missed my first, I went 0 for 4. I'm due for a hit. Are you due for a hit? How many trials is that one bad at bat? 1. Oh, I went to the casino and I decided to put $10 on black. It's probably the best odds you can get in a casino. It's just short of 50-50. Okay? And I lost 4 times. So this next time, I'm going to bet 200 on black because it's due to come up black. That next spin is how many trials? 1. Everybody good? Okay. So the law of large numbers, it basically says probabilities only hold for a large number of trials. Okay. A probability model is not for a singular outcome, but it's for an entire event. So it includes every possible outcome. And its probability. A word we use to describe every possible outcome is the sample space. Okay. Now, if we think about marbles in a bag, the sample space might be red, yellow, and blue inside the bag. But I don't want us to think, and the sample space for this dice might be the numbers 1 through 8, or it could be odd and even, or however we want to define the event. But I don't want you guys to think that probability events and outcomes are strictly tied to events like probability events that you guys are used to. For example, when I go home, I go that way down 3rd Avenue. That is how I get home. Me rolling up to Grandview Avenue in 3rd, and whether or not I get a red light or not red light, that's a probability event. Do you guys see what I'm saying? How about this? How about I'm going to take a random sample and measure something about that sample? That sample in and of itself has probability attached to it. Okay. So, the probability of everything in a sample space needs to add to 1. In other words, if I'm rolling this dice, right, 1 and 8, the probability of a 1 is 1 in 8. The probability of a 2 is 1 in 8. The probability of a 3 is 1 in 8. What's the probability if I add up every possible outcome? 1. Is everybody good? Okay. All right. Lastly, we have something called a complement. Complement basically is a complete thing. So if I tell you that the probability of rolling a 1 on this dice is 0.125, because that is 1/8, what's the probability I roll a not 1? Seven eighths or 0.875 or and what so like the probability an event doesn't occur is 1 minus. That ends up being quite useful when we start getting to more complicated probability questions. All right. So I have an example for you. So the event we're describing is randomly selecting a adult student from a university. This is the probability for each age group. Okay? So, if I want to know, is this a complete probability model? First of all, is every age represented here for an adult student? And if I know for sure, if I want to double check, what should all of these add up to if it's everybody? 1. And they do. All right. All right, so what is the probability that somebody's age is between 18 to 23? If I asked you to find that probability, what would you say? 0.57, yeah? Because that's just this range. What if instead I asked you the probability that somebody's age is greater than or equal to 30? What would we do? Add the 2. What if I ask, what is the probability somebody's in the 18 to 23 range and the 30 to 39 range? 0. It can't happen, right? If I were to ask you, what is the probability I roll an odd number and a 2? That doesn't, it doesn't work, yeah? Okay? All right. So we call 2 events mutually exclusive if they cannot occur at the same time. And the probability of what we call their intersection would have to be 0. The probability of the and question. Is there a difference between saying what's the probability I roll an odd and a 2 versus an odd or a 2? Do they mean different things? You guys have talked about and or a little bit, right? Or is adding, and is kind of multiplying, kind of, not really. Okay. So, what are some examples of mutually exclusive events? We said 2 and odd. Somebody got another one?
3 and even.
3 and even. If I'm dealing with cards,
Heads and tails.
black and heart. Right? In a deck of cards. Heads and tails can't happen. Everybody good? All right. So really, when we go up here, the fact that we could add these two probabilities together actually relies on the fact that being 30 to 39 is mutually exclusive from being 40 and over. Okay. So, we have two events. Person's blood cholesterol being 240 or above, and a person's cholesterol being 200 to 239. Is this the sample space? Is this every possible outcome? There's two ways I know that answer. One, is it possible somebody's cholesterol is below 200? Sure. And how do I know that? When I took the two probabilities and added them together,
It's not one.
it's not one. So there's another group that represents everybody else, yeah? Okay. Are the two events mutually exclusive?
Yes.
Let's see. Can somebody, we're really saying, can somebody have cholesterol bigger than 240 and in the 200 to 239 range? That doesn't seem possible, does it? So these events are mutually exclusive. So what is the probability of A or B? Which in this particular scenario, I would call that the probability somebody has high cholesterol. Yeah? What is that probability?
0.45.
How are you getting that?
Add 0.6. 0.16 and 0.29.
All right. So, what is the probability somebody's blood cholesterol is lower than 200?
Everything else.
Lower than 200 is the complement to having high cholesterol, right? Okay, it's the everything else, so we do 1 minus the 0.45. So a lot of what's going to happen with this section, guys, is we're going to have to recognize, that those two things are opposites and applying that. This is a great place to stop. Okay, there's so many different approaches you can take to probability, and we have to use different tools at different times. Okay, so the first probability tool outside of just the how many out of my total is a two-way table. And two-way tables do a really good job if you have raw data to summarize them and organize everything you know. Okay, so if I asked you, according to this two-way table, I want to talk about one more thing real quick. So, have you guys seen these symbols before?
One's or.
One is or. Does anybody know which one's which?
Right or reference A.
This one's or. This one's and. Okay. For and, it'll help you remember it. If I drew a line across, it would make an A to help you to go with and, if that helps you keep it straight. Hello? I sure can. Bye. Bye. Okay. We're gonna discuss one more in a few minutes, so I want to just kind of get it over with. A vertical line means given. So we would use given. We would use that if we know something has occurred. Okay. So if I ask you, according to this table, what is the probability that a randomly selected adult has a pet and walks more than 5 times a week? So one of the things I haven't emphasized a ton yet, but I want to because it's going to make our lives a little bit easier, is we can define a probability event with a capital letter. So I'm going to let has a pet be the capital letter P, and I'm going to say no pet is P with a complement. So typically we might read this as P complement or not P. Everybody good? And then I would call this one W and W complement. Now, what is the probability of P and W? I'm going to need a little bit more than that.
33 out of 58.
We would take 33 out of 58. And you got 0.57? Lovely. Okay. All right. If we know that a randomly selected adult has a pet, so we're given that they have a pet. You guys see that where that vertical line comes in? Okay. We want to find the probability of walking given that they have a pet. And this is the notation we use for this. Okay. So if I'm given that this person has a pet, are you guys with me? That I know we're only talking about this column. Everybody else doesn't matter now because everybody else doesn't have a pet. Is everybody good? So, what fraction do I use? Okay. Would you guys be comfortable with me saying that this box is the P and W box? Okay? So the fraction for this given, this what we call a conditional probability, was W and P over just the total for P. Is this okay? So the reason I'm emphasizing using these symbols and these capital letters is on the AP exam and on your tests, you will get a formula sheet. The first formula on that formula sheet that you're going to use for probability says this: the probability of A given that B has occurred is equivalent to the probability of A and B over the probability of B. Like I said, you're going to have this formula on the formula sheet. So now if I'm looking at, say, this next one, we know a randomly selected adult walks more than 5 times a day, or 5 times a week. So we're doing the probability, given that they do all that walking, what is the probability that they have a pet? So the top of that fraction would be pet and walk, which is still 33. What would the bottom be?
41.
Walking. Point
That's nice.
0.79 something.
0.8.
32 out of 40 would be perfectly 0.8. It's probably 0.804. Lovely. Okay, everybody good? So far? Okay.
Do you want to, what do you want us to round to, like,
Probability typically 3
okay.
is enough, typically. Okay. And these ones are both what we call conditional probabilities. They are conditional in that something has to have occurred first. This one has 2 pieces of uncertainty. So it's going to have a lower probability than either of these, which only has 1 piece. Like if I look at this, I know this has happened. This is the one that I'm uncertain about. Do you guys see what I'm saying there? Okay? All right. So I got to do one more because it's on your homework. Or on your quiz review. You guys, what is the probability of W or P? Okay, P over the total would be 33 out of 58 plus P over the total would be 44 over 58. Yeah.
Plus 40.
44 out of 58 plus 41 out of 58?
Minus 30.
And then you have to do minus 30.
Okay, great. Why do we have to subtract the 33? The 33 was included in this total, and the 33 was included in this total. It can only be included in one of the 2 totals. Okay, second probability formula. The probability of A or B is equal to the probability of A plus the probability of B minus the probability of A and B. We can kind of see it here because those 33 people got counted twice, yeah? All right, now up top, we did the probability of A or B and we just added the 2 probabilities. We didn't subtract anything. Why didn't we subtract anything here?
Nothing overlapped.
I'm sorry?
Nothing overlapped.
Yeah, those 2 events, having the super high cholesterol and having the borderline high cholesterol, were not were mutually exclusive from each other. So their overlap was 0. So technically, we should have subtracted 0 at the end, but it's 0, so we didn't. Everybody good?
So if things are mutually exclusive, you can't have a table like that?
The value inside the table would be 0. Everybody good? Okay. Page. Oh, before we do that, all right, next I want to talk about the multiplication rule. And to talk about the multiplication rule, we're going to, I want you to imagine we're going to do 2 dice. We're going to roll it. What is the probability of getting a 1 for the first roll and getting a 1 for the second roll? How would we do that? What is your brain, what is your intuition telling you to do? 1/6 times 1/6. That you would multiply those 2 probabilities, yeah? Okay. Now, what if instead I'm randomly selecting one of you? No, 2 of you. I'm going to randomly select 2 of you to get extra credit or something.
Two at the same time or one then another?
It actually doesn't matter.
Okay.
I want to know what is the probability that the first person is wearing a hood and that the second person is wearing a hood. The 1, 2. Is there a hood on that, Kate?
Yeah.
3, 4, 5, 6, 7, 8 out of 11? 8 out of 11?
We do a replacement?
No. So the probability that the first person I select being in a hood, having a hood on, would be 8 out of 11. All right, I selected one of you. Now I got to select the next person. What's the probability that person is wearing a hood? 7 out of how many? 10. Because no matter what, I have one less person in a hood in the room. And one less person in the room once I've selected you. Yeah? Everybody good? Okay. So, and events in general. The probability of A and B occurring is equal to the probability of A occurring times the probability of B if A has occurred. Okay?
Wait, but if it's 7 out of 10, how do you know it's 7 out of 10? Because if you picked,
Because the first event has occurred. The first person I picked was wearing a hood.
how do you know?
It's saying what are the odds?
Because when I'm saying, what is the probability this happens and this happens? So
Uh,
this already happened to get to this one.
So is it kind of like saying what's the probability that the second person had a hood given that the first person had a hood?
That's what this number is. Yes.
Okay.
Hence, this is you multiply by the condition. Okay. And you guys, this one, not on your formula sheet. What is on your formula sheet, though, is the probability of A given B is equal to the probability of A. I'm sorry. And this is the one on the previous page. You don't need to rewrite it down. I just want to show you how it matches up. That if I were to isolate this, I'd multiply this time these two things, yeah?
So if you flip the A and B, the bottom would be.
Which A and B are arbitrary letters just in their spot anyway, okay? So you could still fill into this formula and figure stuff out. Now, the multiplication rule is, we tend to really emphasize it when we use what is Ms. Meister's favorite probability tool, the tree diagram. Now, tree diagrams are annoying. I'm not going to pretend they're not annoying to draw. They are. They're also super informative and they can help us sort through things. Okay. So I'm going to let you guys read this real quick. And then we'll kind of talk through what about this problem would make me want to use a tree diagram on it. Can you guys even read that? Is it too faint? Sam in the back, can you read this or is it too faint for you?
I can read it.
Okay. I'm going to leave these up so that we can keep referring to them and not have to keep going back and forth in the slides. That was all of them, right, so far? Okay, great. Okay, are we ready to talk about this one? All right, anybody overwhelmed just reading this? Everybody else is lying. You're literally not the only one. I promise you that. Because if I were to then ask you guys, what is the probability that somebody tested positive right now? I'm certain if I asked you guys to solve this question, you would say, I don't know how to do this. So you are a little bit overwhelmed. That's okay. The tree diagram is to help us answer questions like this where, I don't know about you guys, but I see a lot of percentages and a lot of context, and it's really hard for me to kind of make sense out of this. Okay, you guys. I want to start with the phrase false positive. What does a false positive mean?
It says it was positive, but wasn't.
Okay. The test came out positive, but the person did not do drugs. Are you guys with me? So in other words, both of those things had to happen. So I'm going to call the false positive didn't do drugs and tested positive. Oh, no. Hold on. We know the person didn't take drugs, but they tested positive, is the way to think through that. Because the fact that we're attaching the point, or the 1% means we don't know whether the positive happened or not. It'll happen 1% of the time. Okay. And likewise, false negative would mean we know they took drugs and they tested positive, or they tested negative. Okay. So as we go to build our tree diagram, the first thing about our tree diagram that we're going to use is this idea of we have two different sets of numbers, one for somebody took drugs and one if somebody didn't. So my first branches on my tree diagram need to include took drugs and then didn't take drugs because those are the ones I'm trying to isolate from each other. All right, so those are my types of individuals, and then they take this test, and what are the possible results? Positive and negative. So they could take drugs and get a positive test result. They could take drugs and get a negative test result. That's half of my possible outcomes. But they could also not have taken drugs and gotten a positive test result. And not have taken drugs and got a negative test result. Are we feeling okay still? Now let's put in some probabilities. What do we know? Do we know anything about these probabilities?
2%.
2% is, so the probability of this branch is 2%. You guys comfortable with that? So what I'm going to do is put a 0.02 over that branch. And then, hold on. If 2% of people didn't take drugs, right? How many people, 2% of people use performance-enhancing drugs.
98%.
98% didn't. So how do you guys feel about me saying that the set of branches should always add to 1? Great, lovely, wonderful. Okay, now, the minute I get here, this is a different set of people, a different set than here, and each set has different rules. Here's what I know up here. If I know that they took drugs, the probability that the test comes out negative is 0.5%, which is 0.005. Everybody good? 0.5%, percents to decimals, we move it over 2. So what does that make this? 0.995. Perfect. Everybody good? What about if they didn't take drugs? What do I know? Probably they test positive is 0.01. And then, I don't know, 0.99. Okay, so this branch would be D and positive. This would be D and negative. This would be D complement and positive, D complement and negative. Are you guys with me? That we now have every single possible outcome for this. And what we can do, because we have that multiplication rule, we multiply probabilities to get the end result. So, can we do 0.02 times 0.995 real quick? And if I'm not very smart, but let's see if I can get there. How'd I do?
Yeah.
Fine. See, I'm not very smart. You shouldn't even trust me. What should all four of these add up to? 100%, yeah. And they do, yeah. You guys, if I look at just these branches, are you guys with me? This is everybody who used performance enhancing drugs. Is everybody with me? So what should the total of these two branches be? 2.02. 2%.
Yeah.
Everybody good? Are we seeing it? These add to 0.02, these add to 0.98. Everybody good? All right. Which outcomes if I wanted to find just the probability that somebody tested positive, what would that be? Add together the first number and the third number. So we would do 0.0199 plus 0.098. 0098. And I think we get... Okay, what does this mean? Of all the athletes tested, just under 3% are going to test positive. We feeling okay? Because this is just the probability positive. This is like, these are the ones who took drugs and tested positive, and the ones who didn't take drugs and tested positive. Are we feeling okay? Man, that's not very many people. You guys, when you saw, say, this false positive rate and this false negative rate, does this make you think that these tests work pretty well? Yeah. And in fact, we could look at how often does the test come to a wrong decision, and that would be what? Here and here, which is like a really tiny amount, right? Is everybody good? Okay. So I agree that these tests work really well. There's something a little bit funky going on here, because there's something else that jumps out at me that might not jump out at you guys yet. All right. So you guys know that anytime you meddle they automatically give you a drug test. We good?
Yeah.
Okay, so let's go ahead and say you want a medal. You test positive for performance-enhancing drugs. Does that mean that you used performance-enhancing drugs? No. So I want to know, given that you tested positive, what is the probability that you actually took performance-enhancing drugs? So as we think through this, using the conditional probability formula, this one, for those of you at home, how does that translate to this context? What would the top number be?
0.01.
I'm just going to do it in symbols for now. It would be D and P over P. On a two-way table, this formula is very intuitive. On a chart, not so much, or on a tree diagram, not so much. Okay, so let's go ahead and do this. What's D and P? D and P was 0.0199, and the probability of testing positive was 0.0297. It's all the people who tested positive?
Yeah.
Okay. Is everybody good? You guys, did you get 67%? Roughly 2/3? Okay. 2/3 of the people who tested positive actually used performance-enhancing drugs. You guys, if you're one of the other third, wouldn't you want this number to be a lot higher?
Do they test you again?
So, you guys, they rarely publish if somebody tested positive once. The minute you test positive, they test you again. They take a different blood draw and they test you again. You have to test positive usually 3 times before anything gets publicized. Because even though, and this test is good, you guys, it's good. It's just that what happens is, because so few people actually use these performance-enhancing drugs, it doesn't matter how good the test is, you're still going to have a little bit of a margin here. And the more different these two numbers are for each other, the more crazy this is going to feel. Everybody okay?
Are these real?
Yeah. These are the real numbers from the Beijing Olympics in
Do you
2008.
lose your medal, I'm guessing?
Yeah. I'm sure there's some
What percentage of people that won a medal that were?
that I don't know. I know that when it comes to the medalists, it's very, very small, because going into it that you're at least in contention. You're very few people, if that makes sense.
Why don't they just test them right before?
The problem is there's tens of thousands of athletes at the Olympics, so it becomes a cost and efficiency question of should you be testing. They do test a random sample of people coming in, and they certainly that's why we've seen in the past few years certain delegations not being allowed to compete, because literally the whole delegation or everybody from a delegation that was sampled showed use of performance enhancers. I think it's an interesting question. Okay. Next, you guys, we're going to jump from drug testing into melons. We're only going to do part A today. That doesn't feel like a big jump, does it? Only if they somehow injected performance enhancers inside the melons or something. But that feels pretty crazy. Okay. So, Do you guys understand conceptually that there's different distributors of different things?
Yes.
Okay, great. So we have two different distributors of these melons. Obviously, you guys can see this is a relatively recent free response question. I say anything in the past 10 years is pretty recent. Like, I remember when my students answered this question, so I would call that recent. Okay. And for part A, part A is actually nothing to do with the tree diagrams that we just learned, but parts B and C that we talk about tomorrow will be. Okay. It says, for a melon selected at random from distributor J, what is the probability that it's greater than 137 millimeters? And what we know about distributor J is approximately normal with a mean. So if we have approximately normal, that means I can draw the approximately normal with a mean of 133 and a standard deviation of 5. All of this is given to me in the stem of the question. And I'm going to go ahead and label this with a J because this is distributor J. Okay, and I want to know what is the probability that I get something from distribution J that is bigger than 137. That's what we're basically being asked to find. Here's 137. So that's my boundary. And am I shading right or left here?
Right.
Right. Does anybody remember how we put this in our calculator? It's been a while, for sure. Not in the stat menu. It's in the distribution menu. So if you hit second and then vars, you're going to choose, in this case, we would choose normal CDF. Okay? When it asks for the lower and the upper, it's asking for the boundaries of what's being shaded. My lower shaded boundary is the 137. My upper is gajillion, some really, really big number. The next symbol it asks you for is that curly Q, M for the mu, which is the population mean. And then this is my standard deviation.
Wait, what's our upper?
A gajillion, some really big number. It should be around 21%, 0.21.
Yeah,
We're starting to get a different probability tool in that distributions menu in our calculators can be quite helpful. Yeah. Your standard deviation is 5.
Oh.
Everybody good? This is a good place to stop. We won't have time to do the other one, and I'd rather do parts B and C in one fell swoop.
Were there notes from yesterday?
Yes. I haven't uploaded them,
Okay.
but I will. I'll do it right now because 7 period is taking the test. And